So this video is about the Doppler effect and defining what it is and looking at a visualization of how waveforms change when a source of waves or an observer moves. You should have watched a little blurb from YouTube on the basics of the Doppler effect. Now we just kind of want to formalize the concepts behind it, look at some applications, and then we're going to derive some equations that essentially tell us what kind of shift in frequency or wavelength one can get when we have this phenomenon occurring. It is fairly widespread in nature. It has tremendous applications, not only for weather systems, but in medical imaging and even in astronomy. Some of the most important discoveries of the past century have come because of, in part, of using the Doppler effect. So to give us an idea of the Doppler effect, we're going to get waves a little slightly differently than we had before. Instead of looking at one-dimensional wiggles, we're going to look at it from a two-dimensional standpoint, essentially ripples in a pond. So if you look at the diagram we have in front of you, it looks like a bullseye. You can imagine you have a source somewhere in the middle that is creating vibrations, and those vibrations are propagating out in time, where the distance between each crest, let the dark part represent a crest, is a wavelength. Okay, so we have 1, 2, 3, 4 waves have been created in this snapshot that we have. Okay, so in a non-moving source, you will notice that the wavelength of the ripples is the same in all directions. Okay, the waves rarely, and it's very difficult to propagate in one particular direction. So if this is a surface of water, it'd propagate in 2 dimensions. If this was sound, it'd propagate in 3 dimensions as a sphere. But regardless, you would have equal wavelengths. Okay, and if you're an observer, whether you're at point A or point B or anywhere else in that field, you would just detect the same frequency regardless of where you stand. All right, so if I'm standing right here at B and I have something hitting me, it would be a regular frequency depending on the source and the medium through which it travels. All right, now let's change things a bit. And this is where the Doppler effect comes in, so we're just setting things up. Now let's say our source of waves, this blue dot right there, starts to move to the right with some velocity u. Okay, so we're going to use the term, or the symbol u, because we'll see later on when we do equations. So it's moving forward with the velocity u to the right. We got 4 observers standing around this. We have A to the left, B to the right, C and D off to the sides a little bit. So it should be pretty clear to you, based on this diagram. This is a snapshot after 1, 2, 3, 4, 5, 6, 7 wavelengths, 7 periods have gone by, that the waves are scrunched together in the direction towards B, and they are further apart than normal in the direction of A. And if you go in the direction of C, notice that the spacing is more or less the same. And it's the same as the original. So there is a shift in what the observers see, or hear, or detect. And that's what the Doppler effect is, okay? So observer B will detect wavelengths that are closer together, i.e. a shorter wavelength. And if the wavelengths are closer together, it's going to be a higher frequency. So instead of the ba-dum, ba-dum, ba-dum that we heard from the original waveform, we're going to hear ba-dum, 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 ba-dum. And A is going to detect just the opposite. So A will hear a ba-dum, 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 a lower frequency and a longer wavelength. How about the speed of the wave? If our source is moving, will B detect a faster speed, and will A detect a lower speed? Well, if we go back to our previous lesson, what does speed depend on? It doesn't depend on the source. It doesn't depend on frequency or wavelength. It depends on the medium. The medium's not changing here. Whatever the wave is propagating through is staying the same, even though the source is moving. So the wave will remain the same. That's important. All right, so let's define this phenomenon. It's called the Doppler effect after I believe it was Austrian or German physicist from the 19th century, Christian Doppler. Okay, so what is it? You need to know this definition. All right, there's a lot of subtlety to it. So it's the apparent. Okay, I'm going to use another word for that. I'll put in parentheses. observed shift. Okay, so it's not an actual shift in frequency. If you are that source, and let's say you're putting on a sound, a siren, and you're in a car, let me step back, you're in a car that has a siren blaring, and that car starts speeding forward, you will hear the same frequency because you're not moving relative to it. So there's no real shift. But if I'm outside the car and the car is coming towards me or going away from me, I will hear an apparent shift. It's what I observe. And what are we talking about a shift in? Well, more than anything, we talk about a shift in frequency. But it's just as well wavelength. They go hand in hand. Okay? Due to, this word is very important, relative motion between the source of waves and an observer. Oops. Okay, so there's a lot there, a lot of details. Let me go back up to our picture right here. So let's talk about the, we already mentioned the, sorry about that. We talked about the apparent part. We talked about the frequency. So what's the relative motion? Well, again, let's say we have observer B right there. If B is moving this way with the same speed as you, there's no relative velocity between them. In other words, this guy is stationary relative to this one, so there will be no Doppler shift. So in order to get relative motion, either B is stationary relative to the ground and A is moving towards it, or B is moving away from A, or the source, or B is moving toward the source. So there's a lot of different ways you can get relative motion. And then you've got to look at, like we said, the source and or the observer. Okay, now let's go back to our diagram here. Let's talk about C and D. This is a little bit more subtle. What will they detect? Well, at this moment, let's say C is right here, and this is where the source is. The object is not, if you will, this is the direction C is from there. There is no component of U that is towards C or away from C. So observer C will detect no change in frequency. How about D? Well, D is right here, and U is moving that way, so we could say that there is a component to U that is moving away from D, right? So there's a part of U. If we were to draw a vector, that would be, well, right here is which way it's moving, okay? All right, so if we take that vector, let me extend it out to D, there's a part that's this way and there's a part that's that way. So we can see that some of the motion is away from D. So D will detect a slight, okay, so not a full, so it's not a maximum, a slight shift in frequency because of a component of the speed is going away. All right, I'm not sure what I'm trying to say, a horizontal component, I guess. So, to sum up before we go to applications, if an object is coming towards you, you will hear or see a higher frequency and a shorter wavelength. If it's coming directly at you, it's a maximum effect. If it's coming at you at an angle, then the effect drops as the angle approaches 90. If it's going away from you, then you have a shift towards a lower frequency and a longer wavelength. Okay. In fact, I don't know why I don't have this here, but in terms of sound, right, for B, let's just talk about B, that's a higher pitch. That you should have seen that. And for light, that is a towards the blue end of the spectrum. All right, so light will appear bluer if it's coming at you because blue is a higher frequency form of light or a shorter wavelength. If we're at A, then it's a lower pitch, and if it's light, it will be a redder in color. And that red and blue shift is very, very important in astronomy, and we'll talk more about that. All right, so let's finish up with some applications here. Okay, I'll just talk about them now, and we can go into greater detail in class if you want. So, Applications that you may have run into: radar detectors and speed guns. All right, so if you've ever been in a car, either as a driver or passenger that's been pulled over by the police and they've used a radar gun, what they're doing is sending a wave at your car. When it bounces off, there's going to be a Doppler shift in the frequency, and so when it comes back, there is a direct relationship between how fast you're going and that shift in frequency. It doesn't matter whether you're going away or towards, they can adjust for that. What they can't do is get your speed if you're going by them sideways. So if you ever look at a police car that's sitting on the side of the road and they have their radar gun up, they're pointing it up the road or down the road, not sideways, because it won't work. Same with the speed gun. If you've ever been in a baseball game, they're measuring the speed of a pitch, whether it be softball or baseball. Where do you have to be? You have to be directly behind home plate. You can't get it from the side. Okay. Another common one, we've heard Doppler radar. Okay, so we're detecting weather / storms. If you've got a front, a moving air mass with rotation in it, okay, you can send radar beams into it which bounce off of it, and based on the relative rotation motion, there'll be Doppler shifts, and you can get an idea of how fast different parts are moving, and then you can just translate to different colors and get a lot of information. A very, very powerful technique. In medical uses, you have measure of blood flow. You can send an ultrasound into your blood, towards your vessels, and it'll bounce off the blood cells. You want ultrasound because they're really, really short wavelengths and they're small compared to the blood cells. When they bounce off, there will be a shift because your blood cells are moving. You get an idea of how fast your blood is flowing for various applications. This is ultimately how ultrasound works for, let's say, looking at a fetus's heartbeat or anything else inside the body. Is any movement, you will get a Doppler shift when you have reflected waves. That's pretty cool. From an astronomical standpoint, you have the whole evolution of the universe is based on Doppler shifts, okay? And it's how we determine the rate of expansion of the universe. This is a 2 or 3 period discussion in of itself, which is some of the most mind-blowing stuff ever. But long story short, when we discovered the universe was expanding in the 1930s, because when we observed distant objects, galaxies, they are all more or less redshifted, meaning they were moving away from us, and the only way to explain that is if the universe is expanding. But I'll talk more about that later. And then lastly, something that's really, really, really cool, and it's fairly recent, and that's hunting for exoplanets. Exoplanets are planets that exist around other stars in our solar system. And what we can do is we can look at Doppler shifts in a star's orbit about the center of mass, and from that Doppler shift we can infer that something's orbiting it, and we can get a lot more information. So I'll try to talk to you more about that later. In class, what we'll do is then learn how to translate the Doppler shift in frequency to a velocity. That's a little bit complicated, but we should be able to handle it.